Okay, hello, and welcome back to this next session on NMR, nuclear magnetic resonance spectroscopy, where we'll be talking a little bit about more on the processes that occur within the instrument whenever we're doing the measurements. We've already established that by introducing some sort of magnetic field to our nucleus, we can get a split in the energy levels that are otherwise degenerate. And then the split in the energy levels obviously creates a certain energy difference between them. And analogous to maybe our UV vis or our FTIR measurements, we're able to leverage that difference in energy to try and get a spectral measurement or some spectroscopy out of the sample. We discussed also the idea of these nuclei having spin, and the four nuclei that were of most use to us as analytical or instrumental chemists was sort of looking at hydrogen, carbon, phosphorus, and you could also look at nitrogen to an extent. You could look at sodium as well, although those tend not to really be looked at that much. And so those are the nuclei that we would target. You can measure others which are like which have integer spins, but the problem is it's a lot harder. So usually it's really just hydrogen and carbon are the by far the most commonly measured. Carbon 12 cannot be measured, but carbon 13, because carbon 13 exists at about 1% of the total carbon population of the world. So even if you don't actually add carbon 13 atoms to your sample, most likely there are sufficient amounts of carbon 13 in your sample to actually get a decent measurement, just naturally. And so that means that we can use that as a reliable source of information. But by and large, the most common one is proton NMR, H hydrogen NMR. Typical modern spectrometers have very fast throughput for those. But let's see the difference between the two major types, which is going to be continuous wave and Fourier transform NMR. And so the Fourier transform NMR is going to carry on quite well from the Fourier transform techniques that we used before for our infrared spectroscopy. So here's a side-by-side comparison of the two. So we have continuous wave on the left-hand side, and we have Fourier transform NMR on the right-hand side. What the graph here is showing on the left-hand side is that as the energy of the continuous wave, or the energy gap between the two spin states of the nucleus increases as the strength of the magnetic field increases. And that makes sense because you can look at this delta E. So delta E here is the difference in energy. So usually whenever we see a capital letter delta, it means change or difference or something like that. E being energy is equal to gamma H over 2 pi times B. So gamma here is the gyromagnetic ratio, which is specific to our nucleus, specific to our system. H is Planck's constant, and pi is going to be just the number pi. Now, what this should immediately tell you is that these are all just constants and these do not vary. But B does vary. So that means that this energy gap is directly proportional to the change in the magnetic field strength B. So continuous wave, what it does is you have like, remember that we use the magnetic field to affect this separation of the energy levels. And then after that, we excite the sample with a radio frequency electromagnetic radiation. So in the case of continuous wave NMR, as the name suggests, it has a continuous wave of radio frequency. The radio frequency electromagnetic radiation does not change. It has a continuous wavelength, and its energy, therefore, is going to be the same. Now, what happens instead in this continuous wave NMR is that the magnetic field is changed. So the magnetic field strength is sort of changed around over a very small range, but the magnetic field is increased or it's decreased. And that's how we get differences in our spectra. because different nuclei have different situations. They have different bonds to them, and much like in FTIR before, those different bonds can affect different energy separations. Then in the case of Fourier transform NMR, what we're going to do is we're going to use a pulse of radio frequency electromagnetic radiation, which is going to have different amplitudes. It's going to have different energies, and so it's going to change it's going to interact with different nuclei, basically all at the same time. So this one is much faster. This one is easier to do, actually. It seems more complicated, but that's really just because of the mathematics. But this kind of experiment is the routine now. Almost all spectrometers are done like this, assuming that you can get assuming that your space, like your physical space, is enough, because these spectrometers take up a lot of space. Continuous wave NMRs can be done with very strong permanent magnets, actually. The resolution is not very good, but it can be done. I've seen examples of it being done. But in the case of Fourier transform NMR, you do need a standard NMR setup. And so in modern times, there's really no reason not to use Fourier transform NMR compared to continuous wave, because the information you get here is just so much greater than what you get here. Although this does have its niche uses, and it is the original. Okay, so in continuous wave CW NMR, we fix the wavelength and we scan across the magnetic field, or we can do the opposite, where we fix the magnetic field and scan over the wavelength. Either one is okay. So what happens is, well, they're basically analogous to each other. We get either a magnetic field peak. So at a certain magnetic field, we get an absorption, or at a certain frequency, we get an absorption. So we can use this information to eventually build up a spectrum for our sample. Okay, so an NMR spectrum. So over on the right-hand side here, we have a low resolution NMR spectrum of water in a glass container, and the frequency is 5 megahertz. So what we're doing here is we're seeing the absorption, we're seeing the magnetic field being changed. So this is going to be like a continuous wave experiment. So we can see that as we change the magnetic field over a certain range, we get different absorptions at different points. So we know that the proton or hydrogen is it's a very easily measured NMR element. So that's kind of reflected in this spectrum, where the absorption peak is very strong, at least compared to all of the others. And that indicates to us that it's going to be a very nice nuclei to focus on and to look at for our measurements. Then we can see, as we change the magnetic field strength with a continuous frequency here, the frequency of 5 megahertz for our radio frequency electromagnetic radiation, we can see that the absorption is changing. Or sorry, not the there are absorption events at certain magnetic field strengths. Let's go across here. So NMR signals, so the number of signals shows how many different kinds of protons are present. So i.e. the number of unique protons and carbons. So if we have 5 peaks, that usually means that we have, or 5 sets of peaks, that usually means that we have maybe 5 different carbon, hydrogen environments, or just hydrogen environments in general, if we're doing proton NMR. So maybe we only have 2 or 3, and that just tells us that we have different molecules. Now, whenever I say sets of peaks, that doesn't mean that I have like if I have 5 peaks, I have 5 different types of carbon. Unfortunately, that's not true, because there are things that cause the peaks to split and double. But usually it's pretty clear whenever that's happening. We'll see examples of that as we go through. And then the location of the signals shows how shielded or deshielded the proton is. The intensity of the signal shows the number of protons of that type, and signal splitting shows the number of protons on adjacent atoms. So the location. So usually what we do is we set this spectrum to to zero at a certain point. We have a reference signal. It's usually doped in our NMR solvent. So a very common NMR solvent is going to be chloroform, but it's deuterated chloroform. So chloroform is CHCl3. This is a very, very common NMR solvent, not used. Some species don't dissolve in this. So what we use are different solvents, maybe like dimethyl sulfoxide, DMSO, or deuterated water, things like that. So we deuterate this chloroform. One of the reasons why it's chosen is because it's a good polar organic solvent, and it only has one hydrogen. So it's easy to remove this hydrogen and replace it with deuterium. The reason why that is done is so that we don't get a spurious signal from this, which would like kind of confuse our regular hydrogen spectrum. So CDCl3, that's chloroform, deuterated chloroform, and that is doped with something called TMS, trimethylsilane, or tetramethylsilane, sorry. So that's a silicon group, which has got 4 methyl groups attached to it. So this is going to be our reference. So what I mean by that is that that's going to be our 0 point for our spectrum. And so that's what this location means. So depending on how shielded or deshielded a proton is, we'll talk a little bit more about what that is as we go through, but basically it talks about how, well, yeah, we'll stick with shielded or deshielded for now. And the location, so basically how far away it is from this means it's going to be less shielded. So the closer it is to 0, which so that's equal, so that's our 0 point. 0 point. So all of the hydrogens in that give us a 0. And then from that, we have a certain distance. The intensity of the signal shows the number of protons of that type. So yeah, so the area or intensity of the peak actually corresponds to the number of protons of that type that are present. Usually NMR spectrometers have a tolerance of around about 1%, which means that they have an error of around about 1%. Then signal splitting shows the number of protons on adjacent atoms. Yeah. So this is something I talked about whenever I said the first one, which was the number of different kinds of protons that are present. So oftentimes if we have like protons, in the case of hydrogen NMR, adjacent to each other, what we see is that they'll cause a splitting to occur. So we'll have sets of peaks rather than just an individual peak for each type. But they follow very similar, like the rules they follow are very robust, and they're usually pretty easy to work out the spectrum. So information in NMR spectra. So here is a list of things which can happen. Down at the bottom, we have this peak splitting. We'll get there in a moment. So peak position, we usually call this a chemical shift. In NMR spectroscopy. It's not normally called the peak position. It's normally just called the chemical shift. It's given the letter small delta. So small delta is usually in ppm, and then it's going to be equal to the frequency of the observed absorbance minus the reference frequency over the reference frequency, and all of this is in hertz. And so these references, that's the TMS that I was talking about before, the tetramethylsilane. Then, so what we get here is chemical or electronic environment of the nucleus. So its peak position here depends on what nuclei it's bonded to. So if it's hydrogen, it's going to be bonded to maybe carbon, maybe it's going to be bonded to an oxygen, maybe it's going to be bonded to a halogen. I don't know exactly with the individual samples. But depending on the sample, we're going to see different chemical shifts, different peak positions. And so that's kind of one of the powerful things about this, is that reasonably reliably, at least more reliably than other techniques, NMR has a kind of a set of locations for the peak positions. Okay, and peak splitting. So this has a special name as well, which is coupling constant. So it's given the letter J, and it's going to be in hertz. So this is the peak separation. So intensity ratios And this is all about the neighboring nuclei. So this is not about our particular species of interest. This is about the species which are nearby. So it could be like a hydrogen in a methyl group beside a hydrogen in maybe an ethyl group or something like that. What I mean by that is like this. So say we have, this is a methyl group here. Say it is bonded to this, which is just the backbone of a hydrocarbon. I won't draw everything out. I can draw it out, I suppose. This is propane. So these hydrogens here are going to be different from these hydrogens here. And these hydrogens here are going to be the same as these ones because of symmetry. Because if you draw a line here, down the middle, you've got a mirror plane. That means that these are going to have a different chemical environment to these and these. That's because these are this carbon. So this hydrogen is bonded to this carbon, which is bonded to two other carbons. Whereas this hydrogen is bonded to this carbon, which is only bonded to one other carbon, and the rest are hydrogens. So there's going to be some difference there. Then the peak intensity. So that's going to be, well, actually, to be honest, these two names and these two observables and these two names, they're kind of interchangeable. Usually, like what we're getting here is the integral of the area. So this is what this means is that the area, so okay, relative to the area of the peak, we can get the number of atoms that it corresponds to. So what that means is like the reference peak is based on this tetramethylsilane. So tetramethyl means 4 methyl groups. That means that if a methyl group is CH3, that means there's going to be 12 hydrogens because 3 hydrogens in each methyl group. There are 4 methyl groups, 3 times 4, 12. So that means that the area of this reference peak is going to represent 12 hydrogens. So that means that we can set the area of that peak to 12, and then the area of all of the other peaks will be will correspond to the number of hydrogens in this case that it corresponds to. And so that gives us this peak intensity, this integral. So usually the peaks are more like this, so they're a bit broad. So it's not really just the height, but also the area under the peak that we're interested in. So you take the integral of this area, like here and here, something like that. And then you can get a really nice area under this, and that area will correspond to the number of protons which is there, which will help you a lot in your assignment. So this is a unitless ratio relative height of the integral curve. As I said, height is subjective. I prefer to look at the area. The height is only really relevant if you've got a very, very sharp peak. Like if you've got peaks like this, you can kind of get away with the height only. But if you've got a broad peak like this, then no, that's not possible. Because if you just took the height, you're losing all of this extra information down here, which is real. So this is the nuclear count. So how many nuclei there are. Then the last one is peak shape or line width. So that's the width of so line width LW of the peak. So it's the width at the peak half height. So this is the height of the peak, go halfway, which is here. And that's where you get the line width at the half of the height. So if the height is 4, you get the line width at 2, something like that. So this is all about molecular motion, chemical exchange, uncertainty principle, uncertainty and energy. So some protons or some hydrogens are exchangeable. So that means that they can swap positions, which means that you're going to have differences in your peak shape. Your peak is going to be broader typically, and so on. So, okay, so down at the bottom here, we have examples of peak splitting. So peak splitting was the second one we talked about. So here are examples of peak splitting. So what is happening here is we have this is what is called a doublet because there are 2 peaks. Here we've got a triplet because there are 3 peaks. And here we have a doublet of doublets. So this is like what happens whenever we have our peaks, our atoms adjacent to others. So this is kind of what's happening up in our propane and things like that. So the different chemical environments of the hydrogens will create different peak shapes and peak expressions in our spectrum. And so we can have different ones, and we'll talk about why those are in a minute. The J here is this coupling constant. So that's the distance between the peaks is given J, which is usually reported in Hertz. So that's generally the information we can get from our NMR spectra. And then we, of course, then will compare that information to the species that we think we have and confirm whether or not we actually do have it. So here is our FTIR, or not FTIR, FT-NMR, so our Fourier transform NMR spectroscopy. So we have our sample here between two very strong magnets, and then we have our electromagnetic radiation, which is incident on our sample, and then we detect using the detection coil any sort of absorption events in the sample. Because you remember that what we're measuring here is not really the release of the electromagnetic radiation. That's a very rare occurrence for nuclei absorption. Instead, what we're measuring is sort of like thermodynamic changes and things like that, and changes in this electromagnetic radiation after it has passed through the sample. So during the pulse, what happens is that we have a bunch of unaligned nuclei initially. Then we turn on our magnet, and then they all align either with or against the magnetic field. Then what we see is that we can measure this by passing our radio frequency wave through it. And what happens after the pulse is it relaxes. And so it will, here we have our dipole moment of our molecule, where we're going to be having, so basically what we've done is we've taken these and we've put them here. Could have really any direction. Like it doesn't have to be perfectly aligned, just so long as it's in the general correct direction. I realize now that red is the color of those oppositely aligned, but hopefully you get the idea. It's aligned. This red arrow is aligned with the magnetic field. So during the absorption process, what happens is the dipole moment will absorb some of the electromagnetic radiation, and then this will give it enough energy to change its orientation of its dipole moment to a different direction. It could be X, Y, Z, or it could be even opposite in Z. It's okay. But in this case, we've said that it's going to be aligned with the Y-axis. And then after that energy has been used up, it will return back to being aligned with the original dipole or original magnetic applied magnetic field, this B0. So that process will continue to occur so long as there is electromagnetic radiation available. We will have a nuclei which is aligned with the magnetic field. It will absorb some light, then it will change its dipole moment using that energy. And then after that, what happens is it will relax back to the original state again. And so it's this kind of absorption and relaxation process, which is what we're kind of trying to measure in our nuclei, because remember, as we apply the magnetic field, we're getting a separation of the energy levels. And so that separation of the energy levels is what we're able to measure, because without the magnetic field, there is no separation of the energy levels. And so there could be no NMR spectroscopy. So it can go through various processes. So we've got here the absorbed dipole moment can then process around a certain direction as it's got energy now, so it can move more. So it's able to, it oscillates in an angular momentum of, so this is omega is equal to gamma B. It's always relative to the magnetic field strength. The stronger the magnet, the more energy that the dipole moment gets. So it starts to process, it processes more and more as it gets more energy until such times as the dipole moment is in a perpendicular direction, or it's basically just in a different direction than the original. So here it's flipped, it's gone from the Z-axis alignment to the Y-axis alignment. Then what happens is that then it starts, the energy it's used has kind of been used up here, and it starts to dissipate the energy and return to its original state, which is a lower energy state because it's aligned with the the direction of the applied magnetic field, and we go back to the start again. And then we have to absorb more energy to go through this process again. So basically what happens is it is processing about the magnetic field. It's going around and around in circles. And it's doing this because it has absorbed energy. What we can do is we can detect this as we go through in time. So the frequency then is dependent on the applied magnetic field strength. It's dependent because the applied magnetic field strength, remember, the stronger the magnet, the bigger the separation in the energies. Then it's also dependent on the individual species because these species all have their own gyromagnetic ratios. But so whenever it reaches, we set up our detection coil so that it is going to be perpendicular to the applied magnetic field, so that whenever any nuclei are perpendicular to the applied magnetic field, we're actually able to detect their relaxation process by their dissipation of energy. And then this is kind of like the pulse of a Fourier transform Fourier transform radio frequency. So what's happening here is we're detecting a signal. Oh no, sorry, this is not the Fourier transform. Is it detected signal? No, it's not. Okay. So this is the signal coming from the sample. So whenever it is aligned with the detector, so whenever it is perpendicular to the magnetic field, we're seeing that there is a high amplitude to our wave. And then as time goes by, remember, it goes back up to being aligned with the magnetic field. So it returns back up. This is the reduction in the detected signal strength. Then by using our radio frequency, we can do a Fourier transform on the detected signal, and that will give us a peak. So the Fourier transform is just the mathematical operation which occurs, which then can convert this frequency domain detected signal into, time domain detected signal into a frequency domain detected signal. So we get an actual peak position where our nuclei should be. So it's got a certain ppm, so it's got a certain signal position. We can see then the changes in energy as it goes by. So we have our initial aligned with the magnetic field dipole. Then there is a pulse, a pulse of energy from the electromagnetic radiation, which gives it enough energy to affect a 90-degree change. Then it relaxes back up again. And so you can see that initially there's going to be no signal. Then after this pulse, we see that there's a strong signal here. So that corresponds to here, the high amplitude part. And then over time, it relaxes back to its original position, which is where we have no signal here. Then we have a pulse, which is this kind of rectangle. It represents the pulse of energy, which affects this flipping of the dipole moment. And then over time, it relaxes back to the original state. This is really just the same thing. This is kind of trying to indicate to you that there can be multiple different nuclei which can do the same thing at the same time. So what we were doing there was a single dipole moment, but those dipole moments are actually the nuclei of a molecule. So there's a lot more going on than maybe than just one signal. So there can be a great many different signals, and we can detect all of them and Fourier transform them all to get back to the original state. So we get then the combination of all of them. So it looks something more like this, where we've got constructive and destructive interference. If we remember back to our waves lectures, I think in module 2, we talked a lot about constructive and destructive interference of waves. So then by Fourier transforming this, which is not something we cover here, but it's something very important to this technique, we can get a time domain spectrum and transform it into a frequency domain spectrum where we have different peaks, different heights, depending on just the number of protons or number of nuclei of that type which are present. here is kind of like the hardware of what's happening inside of this. So this is like inside of like a block diagram of an NMR spectrometer. We have our sample here positioned between two being a strong magnet. Usually these are electromagnets, so they can be turned on and off because permanent magnets don't really have the strength to generate enough of a separation in the energy levels to actually measure anything. So we obviously use some sort of radio frequency, which is this, which we pass through the sample using this radio frequency coil. Then we amplify that signal so we can actually measure it in some way. We've got a phase sensitive detector. We Fourier transform this measurement that we've got, and we get a display of certain peaks at certain positions, which are relative to the reference. So folding of a spectral line brought about by sampling a frequency that is less than the Nyquist frequency of 1600 Hertz, and that is sampled at a frequency of 2000 samples per second, as shown by the dots. So we've got the frequency here in Hertz, which we get, this is our frequency domain spectrum, which we got from the time domain spectrum up here. So the solid line is a cosine wave having a frequency of 400 Hertz. So that's going to be our radio frequency wave that we're passing through. And then this is the frequency domain spectrum, which is representative of this folded line here, which has got a continuous wavelength. So it represents just one signal. We're sampling it at different points because the solid line is the representation of the radio frequency that is being given out by our, what do you call this? By our radio frequency generator inside of our NMR spectrometer. The dashed line is the signal produced by the relaxation of the dipole moments of the nuclei that we're interested in. So since it's, as I said, it is continuous and it has one amplitude, it has one wavelength, it gives one signal here. And then of course we can still detect, because there's a frequency domain spectrum, we can still detect the pulsing signal, the signal which is used to probe it. So if we have overlapping dipole moments, we can see different peaks. And so we have here our detection coil. Again, we have our dipole moments here. And a lot of the time, they are going to flip together in unison. And that flipping process is going to just kind of create, well, it's going to create a more complicated signal for the spectrometer. But thankfully, due to the wonders of Fourier transform, we're able to just kind of like decompose that complicated time domain spectrum into a frequency domain spectrum. And so the overlapping of the dipole moments of different strengths means that we're able to just kind of like get a decent signal out of all of and like resolve it into the frequency domain. So we get like peak positions, peak areas for the samples that we're interested in. That's just, oh, okay. So this one is where we can, this all happens very fast in like 10 to the minus 6 seconds, or 10 to the minus 8 seconds. Sorry, it's even faster than that, 2 orders of magnitude faster. So it happens very, very quickly. So sometimes it happens too quickly for us to get an actual decent signal out. So one of the things that we can do is we can increase the number of detectors. This is not always easily done because of the sort of shape and size limitations of our spectrometers. So usually there's just one, but if you have a particularly nice setup, you can have 2. And this then enables us to sample at 2 positions, one position being maybe along the y-axis, the other being along the x-axis. So these are perpendicular to each other, so they're 90 degrees separated from each other. Don't think that's really necessary. Okay. The chemical shift. So this is the peak position, basically. We talked about the idea that chemical shifts and peak positions are going to be important. because that's representative of the sample that we have. The magnetic field creates the separation, but it's the actual molecule chemical environment which corresponds to the peak position of this particular nucleus. So the chemical shift, the magnetic field at the nucleus is not equal to the applied magnetic field. Electrons around the nucleus shielded from the applied field, and the difference between the applied magnetic field and the field at the nucleus is termed the nuclear shielding. So an upfield shift means that it is shielded and the applied field strength must be increased. Low field shift means that it is deshielded. So low field means that it's at like high numbers in our spectrum, and here we have our applied magnetic field here. Then we have an electron which is spinning around this like in the direction of the dipole moment of the nucleus. Then the electrons are spinning in a certain direction, and then these electrons, which are spinning because of the applied magnetic field, if they are near another element, what they can do is they can actually shield it from the effect of the nuclear or from the applied magnetic field. So we see another schematic of it here. We have the magnetic field of the nucleus, which is going in this direction, going in this direction. You can see it passes through here and here through the nucleus. We then have an applied field, which is our B0. But what happens is that this magnetic field surrounding the nucleus is protected by the circulating electrons going around. And so these kind of shield it, prevent the full effect of the applied field from being felt on the nucleus. And I think we'll leave it there. Okay. And we'll come back to this next time. We'll talk a lot more in detail about chemical shifts and different spectra.